Okay, so in the last class, what we have done is we have found out the uh, first order energy correction of a non-degenerate system, a time independent perturbation. Uh, the correction of energy, first order energy correction, we have found out, and we find that the first order energy correction is something like phi n h dash phi n. So this is a first order energy correction, and the corrected energy level or corrected energy En is given by En naught plus this correction factor. So here we have the lambda factor also coming in, so it's became Hp. So this is the first order energy corrected value. En is the new energy, this is the unperturbed energy, so this is the correction factor. Hp is the correction term associated with the Hamiltonian kind of. Okay, now what we need to find out is the correction in wave function. So not only the energy is changing, the state is also changing. So we need to find out what sort of change is happening there. Okay, so what we have to find out, the thing that we have to find out is psi n1, first order correction in the wave function. This is something that we have to find out. So I can write this like this, an identity. Okay, this is something like psi n1, same state multiplied with the identity matrix. So that will give you again the same state. There is no change for that, and you can substitute your completeness condition here. Okay, you have seen this method several times. Nothing but sigma m phi m psi n1. Okay, now this become just like the coefficient of this particular ion vector now. So this is something that we have to find out for getting our psi n1. So this quantity we need to find out, phi m psi n1. What is this quantity? Phi m psi n1. If you know that quantity, you will be immediately getting what is this phi n. Yeah, phi n dash, first phi n1. Okay, so how do we find out this? Okay, we know one thing about the definition of phi m. That is our initial definition, that this vector phi, let's take if you take the product like this, phi m, what it will produce? This is going to be, if you this is something that we know because it's an ortho normalized system, so it's nothing but delta Ij. We have seen that this quantity is going to be delta Ig, sorry, phi m, when phi m is coming, it's not delta Ij. Phi m is coming, it is nothing but 1. When they are different, you are going to get 0, like that. So this quantity is phi m is 1, and phi n is going to be 0. So this is something that we know. Okay, what about phi n psi n? What does this mean? Phi n and psi n. So this is our unperturbed ion vector of our unperturbed Hamiltonian, and this is corresponding to the perturbed Hamiltonian. So we are taking that the perturbation is very small, it's really small, so there is not going to be very significant change for this particular quantity over there. So it's going to be more or less like whatever you are getting when you are putting phi n and phi n. There is slight variation. So this is like it's approximately equal to 1. Not much of variation, but slight variation. And if you adjust the normalization a little bit, you will be getting this quantity. You can adjust that as a precise one, no issue on that. So this can be taken as 1. Phi n psi n is going to be equal to 1. Okay, what is this phi psi n? What is this quantity? This quantity is nothing but our phi n plus, this is actually the power series of in terms of lambda, that is lambda into phi n plus lambda into psi n1 plus lambda square into psi n2 plus etc. That is this quantity phi n. So I'll substitute this fact over the previous expression, so it will become phi n. I'm substituting for phi n these quantities. So first term is nothing but phi n. The first term is phi n, and another term is phi n multiplied with the psi n1 plus one lambda term will be the lambda square into phi n multiplied with the psi n2 etc. Okay, so we know this entire term, whatever we are multiplying here, that entire term, this term is equal to 1. So this is equal to 1. What about this phi n phi n? Phi n phi n is also equal to 1. Phi n phi n is equal to 1, and phi n psi n more or less equal to 1, and we are taking it as 1. So this is equal to 1. Here this is equal to 1. Then what about the remaining terms over there? That is nothing but 0, right? Whatever coming later onwards, it's going to be 0. So that will give you something like whatever coming later is going to be 0. So whatever are coming later, the terms which are coming later on are phi n psi n1 is equal to phi n psi n2 etc. is equal to 0. All these quantities are equal to 0. That means if you're taking the inner product of phi n with this quantity over the bracket, the correction terms, right, the associated correction terms, first order, second order, third order, etc., etc., you are going to get a 0 value. That means there is no projection of these correction terms along phi n. If there is any projection along this particular phi n, then that will give you, see, that is how it is, right? So let's take just some vector like a, b. If you take a dot b, so if there is any angle between them, if there is a projection value of for b over a, that will give you some non-zero number kind of. Only when this b is perpendicular to a, this quantity is going to be equal to 0. So same way, all these correction terms are actually, if you're taking, this is like this quantity phi n is going to be one vector among them, and phi n dash or phi n1, phi n2, etc., or another term something like this. But what you are getting is, when you are taking this kind of a projection value, what you are going to get is 0. That means all these corrections are not on the same direction of phi n, all are perpendicular to it. That's a whole point. So the corrections are correction terms which are coming are perpendicular to this and vector phi n. Okay, so we got this result phi n dash phi n 2 etc etc are going to be equal to 0. So what we need to find out is not exactly the same. We need to find out something like phi m psi n 1. So one thing we know is that here our m values are varying throughout the space, right? It will take from the lowest number to the highest number, and entire phi m if it is running, and that is the time it is going to give you an identity matrix. So this will contain all the possible numbers. So here we have phi m and psi n. So of course this m covers this n also. At some point of time this m is going to be equal to n, and that kind of a condition is coming since the sigma is there. So you know that whenever phi m equal to, or whenever this m is equal to n, at that time this quantity is not existing, right? Whenever you are taking the projection of one phi m, and you have seen that result already, and this quantity is going to be equal to 0. So whenever m is equal to n, this quantity is 0. So that quantity is having an existence only when m not equal to n. So that is the result that we are getting right now. So let us write it explicitly here. So what we found out is what we got is psi n 1 is equal to sigma m not equal to n phi m psi n 1 into phi m. So this is our phi n dash kind of. Again we need to find out this term. Only thing what we got is m is not going to be equal to n. If that is equal to if both are equal, then there is nothing. It's that term will not be there in that expression. But we need this fact actually. This is not going to be equal to 0. That's why we are explicitly putting it on the expression. Okay, now where we have to go right now is to our previous expression. So we have found out whenever we compared the lambda power 1, we found out the first order energy correction term, wave function correction term in an expression something like this. That expression is like h naught multiplied with the psi n1 plus h1 multiplied with the psi n0 or phi n0. Let's see, phi n. Okay, that is phi n, which is equal to en0 psi n1 n0 phi n1 plus en1 phi n0. Phi n0 means psi n0 means phi. Okay. Okay, now in the previous case for finding out the energy correction, what we have done is we have multiplied the entire term with phi n. When you multiply it with phi n, you got a phi n factor here. A bra phi n you multiplied, so that will become a bracket of phi n, and that will become 1. So you'll be getting en1. Now what we are doing is we have done the doing the same process, but we are multiplying it with the phi m. So the expression is multiplying with the phi m, bra phi m. So you can see what happened now. So this will modify the equation like this: phi m h cap phi m h cap psi n1 plus phi m h1 phi n, which is equal to en0 into phi m psi n dash, right? en0 phi m into psi n. Okay, next term is en1 into phi m into psi n. Okay, that we can do. So if I multiply with phi m from here, it's phi m into phi n into en1. So what about our m and n? Right now we have seen that m is not going to be equal to n for the case that we are interested. So we are not going to have that particular term. So we are only bothering about whenever m and n are not going to be the same. So when you are multiplying this term with a phi m factor here, we know that m and this n is not going to be equal to 0. So this product in that case will be having only by value 1 when this m and n both are same. If both are not same, that term is going to be 0. So phi m phi n is going to be 0 because m and n are different. So we need not to put that term there. So our entire equation is this much only. There are only two terms. Okay, now what we can do is we can apply this h naught, right? We'll apply this h naught to phi m, and what it produces is nothing but em. It will produce em naught. Em naught it will produce, and phi m psi n 1 will be there, plus phi m h dash phi m, which is equal to en0 again phi m psi n1. Okay, here phi m and psi n1 are common on both sides, and you can take it together. So that will give you phi m. Okay, let me write it like this: phi I'm taking this term that side. This will become h cap dash phi m. Oh, okay, this term is phi n. Here it is phi n. This is n phi m h dash phi n, which is equal to en0 minus em0 multiplied with our phi m psi n1, or phi m psi n1 will give you phi m psi n1 will give you phi m h dash phi n divided by em naught. Oh, en naught minus em naught. So this is the quantity phi m psi n 1 that we need to find out. So we got the value corresponding to that. So if you know that, you got it. Okay, so what we got is psi n1, because psi n1 is equal to sigma m not equal to n, this quantity multiplied with the phi m psi n1 multiplied with the phi m. Because of that, we can put this value here. It will become like sigma m not equal to n phi m psi n dash. We'll substitute the value phi m h dash phi n divided by en minus en0 minus em0 into phi m. So this is going to be the first order correction in wave function phi n1. This is our 12th equation, right? Okay, 12th equation is the first order correction in wave function. I think it's 12th one. Okay, I'll put it on a rainbow box. Okay, so that is our first order correction wave function. But about our corrected wave function? Corrected wave function is psi n is nothing but phi n plus lambda into first order correction, lambda into psi n. That will give you phi n plus lambda into this term phi n1, that is this term, lambda multiplied with h dash will give you hp, right? That is a correction in our Hamiltonian. hp is the correction term in our Hamiltonian, hp kind of. So that will give you phi m hp. I can write, you can write it in both way. If you are putting lambda explicitly, you can write it in terms of h dash, or otherwise you can write it in terms of hp. Use lambda phi n into phi m, that is okay. So this is our final expression for the corrected wave function. Okay, so we have discussed the first order correction in wave function and the final wave function form. Now what we have to do is to find out the second order correction in energy, and we are not going to deal with the second order correction in wave function. We'll be discussing just the second order correction in energy, and then let's see how that series goes, and that will give you an idea about the convergence of the series. So we have to see what kind of conditions has to be satisfied. Okay, here the sigma term we missed. So sigma m not equal to n. So those things we will discuss on the next class. I will stop here. So we have to do the second order correction of non-degenerate perturbation theory. Okay.